For our final project for computational fluid dynamics, we chose to discuss how heat can be modeled using ANSYS Fluent. Heat transfer is a very important subject that is studied by engineers and can be found all around us. Heat transfer can occur in an example as simple as a coffee cup warming up when coffee is poured in, or an example as complex as a heat exchanger using a bank of tubes to improve heat transfer. In this presentation, we will model heat transfer using CFD. Our team is made up of Jenna Duvall, Thaddeus Tiller, and Christian Dick. The things that we hope to address in this presentation cover all aspects of computational fluid dynamics in a way that people that are new to using ANSYS Fluent can understand. Our first goal is to describe the fundamentals of fluid dynamics and then use this information to describe the role of CFD programs in the industry. We then hope to apply these details to model a problem that utilizes heat transfer. We will then provide problem specs as well as a simple explanation of the results and modeling techniques that we used. CFD relies on the fundamentals of fluid mechanics to produce results. The equations for the conservation of mass and momentum utilize partial differentials and coupled equations, making them nearly impossible to calculate analytically or by hand. Using CFD and programs like ANSYS Fluent allow for computer-based calculations to be calculated to solve these types of problems. CFD is used to predict the pattern and behavior of flow as well as the pressure and velocity distribution. There are a variety of examples where CFD can be utilized, but a few examples can be seen on this slide. It can be used to show air or fluid flow over a vehicle. It can show fluid mixing within a tube. It can show blood flowing through a human heart, and it can also mimic a flame in a furnace over an extended period of time. Overall, CFD is a form of testing that can be considered more cost-effective as well as time-effective. This problem considers a 2D section of a tube bank. The schematic of the problem is shown in the next slide. This bank consists of uniformly spaced tubes with a diameter of 1 centimeter, which are staggered across the cross-fluid flow. Their centers are separated by a distance of 2 centimeters in the direction and 1 centimeter in the direction. The bank has a depth of 1 meter. The problem that we chose was taken from an ANSYS Fluent practice book and adapted by using our own method of meshing and modeling. We chose not to download the modeling that was provided online because we wanted to do the problem ourselves in 2 different ways. The temperature entering on the left-hand side is 300 Kelvin. The walls of each tube are 400 Kelvin. Our first attempt at modeling will focus on the rectangular section with an area of 4 squared centimeters. This section was chosen because symmetry can be applied to model the rest of the problem schematic. Our second attempt at modeling focuses on the whole bank of tubes. This problem was chosen because of how common tube banks are in heat exchangers. There are 2 types of tube banks that can be found in heat exchangers, aligned or staggered. Staggered was chosen in our problem. The chart below shows 2 different columns of coefficients that can be used to calculate overall heat transfer when using hand calculations. We wanted to approach the problem as simply as possible so that even new ANSYS Fluent users could understand. In the following slides, we will define the variables, determine what is being calculated, model using the Geometry tab in ANSYS Fluent, mesh using the Mesh tab in ANSYS Fluent, use the results and solutions to solve the problem that is being asked, and use animations to model and interpret our results. On the right-hand side of the screen, you can see a screenshot of our geometry. The diameters of each circle is 1 centimeter. The geometry is a staggered bank of tubes. When modeling using ANSYS, we chose to draw 1 circle and then use the copy and paste features to reproduce the additional circles. We chose to model the program in 2D since the problem was a 2D problem. The main component that was modeled was a section of the tube bank that has an area of 4 squared centimeters and that would be symmetrical throughout the tube bank since it can be modeled using this small section. When deciding how to approach the mesh, we first chose to use face meshing. Face meshing automatically determines a suitable number of divisions for the edges of the boundary face. We then chose to mesh the edges of each circle using element size of 3 times 10 to the negative 4th meters. Using sizing makes the meshing application attempt to enforce the chosen divisions. Another method of meshing that we used was refinement and the triangle method of meshing. This produced a mesh that was small and uniform across the body, which we believe would produce valid results when running tests. The meshing that we chose when modeling the small section of the tube bank is the same method chosen when modeling the entire tube bank. The mesh for the small section of the tube bank can be seen in this slide. In order to show the results in every way, we took a screenshot of the pressure and velocity contours in the next two slides. We also chose to model using animations, which will be included later in the presentation. The pressure contour, as seen in this slide, has a high pressure on the two left-hand corners and then distributes across the model, ending in low pressure on the right-hand side. Since our problem focuses more on temperature, we felt as though the temperature contour in the following slide had more importance. The temperature contour slide is one of the most important results slide that we were looking to find. Since tube banks are considered to be fins, they are used to improve the transfer of heat within a heat exchanger. As the water at 300 Kelvin enters the model on the left-hand side, we see that the temperature increases around each tube, which is at 400 Kelvin. The temperature is the highest around each tube, but the heated water continues to flow to the right-hand side after being heated. The results of the meshing of the small area were reproduced to model the temperature contour of the entire tube bank. As stated previously, tube banks are also known as a type of fin and are used to improve the overall heat transfer within a heat exchanger. In the following video, the incoming water of 300 Kelvin is heated by the 5 staggered tubes in the tube bank. As a result, the water is heated by the walls of the tubes at 400 Kelvin, proving the statement that the fins improve the overall heat transfer within the heat exchanger. We chose to adapt a provided problem because we felt we could choose the best method of meshing and compare our results to those published. CFD can be used for solving all kinds of problems that cannot be calculated by hand. As seen to the right, Wolfram Alpha created a widget that allows tube configuration to be adjusted to model different types of tube banks, pitches, and alignment. CFD can help you solve problems similarly.